Okay. So, let me now talk about a very important concept. And this is the concept. So, local thermodynamic equilibrium. Okay. So, this is the topic that we will discuss, and afterwards we will talk about the energy transport in stars. Okay. Now, the first thing that I would like to tell you is that how can you define the temperature of a star? Okay. So, tell me. This I have discussed in many times, right? So, temperature of a star. How can you define? Well, you see, we can define the effective temperature, right? Effective temperature. And this is defined in terms of luminosity. Of course, radius as well, right? Next, we can define the excitation temperature. Which is basically defined by the relative populations of different excited levels of an atom or ion. So basically here we are using the Boltzmann equation, right? So here we have the luminosity, here we have Boltzmann equation. The next is, you see, ionization temperature. Again, this is defined by the relative populations of different ionization stages of an atom. And here we are guided by our Saha equation, right? You see, the next is kinetic temperature. And basically this is defined by the Maxwell-Boltzmann distribution. Okay. Now, there is also color temperature as well. You must remember this, which is basically the temperature of the black body whose spectral, so basically this is black body. So, color temperature is basically the temperature of the black body whose spectral energy distribution resembles most closely of that a star. Okay. So, these are, you see, 5 different ways in which we can define the temperature of a star. Now, you see, except for this effective temperature, which is an important global description of the star, all the other temperatures here, all these 4, they apply to any location within the stellar interior and may vary according to the physical conditions of the gas. So in the center, if the gas density and temperature is high, so if the density is high, here the temperatures will be different compared to the outer regions. Of course, you have to remember that all of these temperatures become the same in the ideal situation of the particles and radiations being in equilibrium. So, all these temperatures become same in the ideal situation of the particles and radiation being in equilibrium. Right. Now, in such a steady state condition, there is no net flow of energy, neither in nor out of any volume element. Right? Nor is there any transfer of energy between matter and radiation. So, every process such as absorption of a photon occurs at the same rate as its inverse process, such as the emission of a photon. Now, such an idealized condition is referred to as thermodynamic equilibrium. Now, a black body is by definition is in thermodynamic equilibrium. But the question is, does this thermodynamic equilibrium apply to our stars? So this is an important question. Now, the answer is clearly it does not apply to our star, because there is a net outward flow of energy through the star. Come on, we are seeing the light emitted from the star, although the very temperature at the center of the star is very high. Basically, what I want to say is that we know that stars are not isolated systems because they emit radiation and also they generate nuclear energy in their interiors. Indeed, the surface temperature of the sun is say around 6000 Kelvin, while even if you estimate the interior temperature from the virial theorem, you see for the sun, surface temperature is of the order of 6000 Kelvin. But if the interior core temperature, and this can be estimated using the virial theorem, I have shown you this, then you will see that this comes out to be around 10 to the power 7 Kelvin. Okay, so what does this mean? This means that the stars are not in this thermal equilibrium. However, it turns out that locally within a star, a state of thermodynamic equilibrium is achieved. So you see, what I am saying is that the temperature varies from millions of degrees in the core to just thousands of degrees in the atmosphere. So, you see, as the gas particles collide with one another and they interact with the radiation field by absorbing and emitting photons, the description of the processes of excitation and ionization become quite complex. However, despite all these complications, we can still apply the approximation of thermodynamic equilibrium, but not globally. So, cross globally. But we can still have a local thermodynamic equilibrium. And this is the topic of today, which is basically local thermodynamic equilibrium. Provided that the typical distance traveled by particles. So, we can have local thermodynamic equilibrium provided that the typical distance traveled by particles and photons between collisions, which is basically their mean free path, right? This is small compared to the scale over which the temperature changes significantly. Okay, now this situation applies to most of the stellar interior where the density and temperature are high, so that the mean distance between the collisions is small. Basically, you can think of this situation as the particles and photons being confined to a local volume. So basically, particles and photons confined to a local volume at constant temperature. You can think of it like that. Okay. Now, let me talk about this a little bit details. Okay. So, what's the average temperature gradient in stars? What can you say? For sun, say for example, what is it? Well, it is quite easy to estimate. Let us do this. You see, dTdr. So, the simplest possible thing we will do is we will take the core and again the solar radius, and this turns out to be 1.6 into 10 to the power 7 Kelvin, and here this is 7 into 10 to the power 10 centimeter. So this is 2 into 10 to the power minus 4 Kelvin centimeter inverse. What is important is this term here, 10 to the power minus 4, and this is central temperature. Okay, now remember this thing. So now in stellar interiors for an average value of opacity coefficient or the capacity of the matter for absorbing radiation, this is basically opacity. I will have a detailed discussion about this later on in today's class. Now so in stellar interior, for an average value of opacity coefficient of the order of 1 to 100 centimeters square per gram and a mean density of the order of 1 gram per centimeter cube, you see we can get a mean free path, and this is given by L is equal to 1 by, this is an important relation. Again, this we will talk about later, and just right now taking something which we will be discussing later on, and you will then after some time you will understand how this is coming into play. Anyway, let me show you the result. The result is that 0.01 to 1 centimeter. This is the result, and this is in outer layer. Well, you see in outer layers this may be larger since the density is very low. This is a typical value. Now what does this mean? This means that you see the relative change of temperature over the mean free path. What is it? Well, so let us find it. So relative change of temperature over a mean free path. What is it? Let's find out. So it is delta T by T. So relative change is basically L dTdr, and again here it is just temperature. Now this is less than 10 to the power minus 4, and this one is 10 to the power 7. So what is it? The value, you see, minus 11, and this is all because of this smaller value of 10 to the power minus 4. Now since over a mean free path L, the relative variation of the temperature is very small, very small. So the radiation field, it can be described by the Planck Law, right, for the local temperature T. You see? Hence, in a small region, basically what we can do, we can define a small region. So we can define a small region, basically a point, you can say, for practical purposes, which is greater than the mean free path L, but much smaller. So it is greater than the mean free path L, but much smaller than the length scale over which significant changes of thermodynamic quantities occur, and this is called as local thermodynamic equilibrium. As a result of this, as a result of local thermodynamic equilibrium, so its result is that we can assume a well-defined temperature distribution inside a star. You understand? In fact, I have discussed about this LT, but not in such details when I was discussing about the various approximations of stellar structure. Before I finish, it is important to note that furthermore, as I am saying, the average time between the particle interactions, or basically, yes, okay, so what I was saying is that along with this, the average time between particle interactions, which is basically the mean free time, which is basically the mean free time, is also, this is much shorter than the time scale for changes of macroscopic properties, and therefore you see the result is that a state of LTE or local thermodynamic equilibrium is secured at all times in the stellar interior. Now, this assumption of LTE, it constitutes a great simplification. This is a great simplification as well. How? Because you see, it enables the calculation of all thermodynamic properties of the stellar gas in terms of the local values of temperature, density and composition as they change from center to the star. So this provides a great simplification in the sense that it enables the calculation of all thermodynamic properties of stellar gas in terms of temperature, density and composition as they change from center to surface. Now, before I finish, it is very important to remember that in LTE we do not have everything. The first is isotropy is not complete. Otherwise, there will be no energy flux going out, right? The temperature T, it changes with distance r to the stellar center, but locally the radiation properties can be described. So the temperature T changes with distance r to stellar center, but locally the radiation properties can be described by Planck's law with appropriate temperature function. Okay. Now in the stellar atmospheres, that is the region where the emergent spectrum is formed, say a few hundred kilometers in the sun, this LT does not apply. So, does not apply. Where? This does not apply in stellar atmospheres. Okay, so these are the three very important points we have to remember about LT.